Welcome everyone. In this lesson, we're going to kind of put everything to use now. So we're going to see how to set up, use derivatives to help us solve applied optimization problems. And to kind of get things started, we're going to kind of look at an easier example, and it's going to really help us kind of set up the different steps that we're going to go through and some of the different terminology that we're going to use. So in this first example, what we're going to do, this is the kind of the entire problem here, is we want to find the maximum value of this function, q equal to x times y, if, or provided, x plus y is equal to 2. So kind of what we're doing here is we're looking for two numbers, x and y, that when we add them together we get 2. And what we're trying to do is we're trying to find the two numbers that multiply together and give us the largest possible result. All right, so we have this problem here where we want to find the maximum value of this function, x times y, provided x plus y is equal to 2. So this is going to be kind of a recurring theme for a lot of these applied optimization problems. Is the first step is to determine what we're going to call the objective and what we're going to call the constraint equations. So first of all, the objective function or the objective equation is essentially what we're trying to maximize or minimize. So if we look at the wording here, we want to find the maximum of this function here, q. So that's going to be our objective function or objective equation, q equal to x times y. Now, the other equation that we're working with, we call this the constraint equation. And this is a secondary equation that kind of puts some restrictions on what the variables can be doing. So if we look, that's what we're seeing with this equation right here. X plus y has to be equal to 2. So if we were just trying to maximize x times y, well, I could just pick numbers x and y as large as I want. But we have this condition here that says you can't just pick anything. You can only pick numbers x and y so that they add up to 2. So this second equation is kind of putting some restriction or putting some constraint on what x and y could be. So that's our second equation. X plus y is equal to 2. And a lot of times with these constraint equations, this is where we have some equation involving our variables and it's equal to a constant. So it's putting some restriction on what x and y can be. They can't just be anything. They have to be numbers specific so that in this case they add together and give us 2. All right. So that's the first step. Identify what we're going to call the objective function or objective equation and the constraint equation. And so in this case, we have these equations already, so this isn't too bad. So what comes next? Well, step 2 is we're going to take this constraint equation and we're going to solve for one of the variables. So you look at the equation, figure out which one is going to be easier to solve for. Is it going to be easier to solve for x, or is it going to be easier to solve for y? In this case, either one be perfectly fine. In this case, I'm going to solve for y just because that's generally what we do. A lot of times we solve for y, just in general, not specifically for these. But it really doesn't matter. I could solve for x here. And when I do it, what do I get? I get y is equal to 2 minus x. So I just move x to the other side by subtraction. All right, so we have our objective. We have our constraint. We've solved our constraint equation for one of the variables. And now what we're going to do is we're going to take this result and plug it in to our objective function. So that's step 3. We're going to plug this result into the objective function. And why this is helpful is because originally our objective of function is two variables, x and y. And we don't know how to maximize a two-variable function. That's higher, that's multi-dimensional calculus, that's Calc 3. So there are ways to do this, but beyond the scope of this course. So we want a one-variable function because we know how to optimize. We know how to find the maxes and mins for a one-variable function. This is Calc 1. All right. So how does this look? Well, we start with our objective, which was our objective function, which what we're calling this function q, but it's x times y. And what we just found is that y is equal to 2 minus x by our constraint equation. So that's what we're going to plug in. We're going to plug in y equal to 2 minus x. So I'm going to replace this y right here with 2 minus x. So I get x times 2 minus x. And then while we're at it, let's simplify this thing down. So let's multiply this out. And we get 2x minus x squared. All right, so that's step 3. What comes next? Well, step 4, this is where the calculus comes in. So we want to optimize that resulting function. So what was our function? It was q equal to 2x minus x squared. So how do we optimize a function, a one-variable function like that? Well, this is what we saw in the last lesson. We find the critical numbers, and then we classify the critical numbers. We test them. So let's find the critical numbers for this function here. So that means first thing we need to do is calculate our derivative, so q prime. And let's differentiate this thing. So when we do that, and I'll use function notation here. I guess I could just leave it as q prime, but q prime of x. Differentiate here, I get 2 minus 2x. And then we look for where the derivative is 0 or where the derivative is undefined. And my derivative here is a polynomial. There's no division by x. There's no natural logs. There's no negatives inside square root functions. So this thing's always defined. So no contribution here from the derivative being undefined. But we are going to get something for our derivative being equal to 0. So we set our derivative equal to 0. So 0 is equal to 2 minus 2x. Solve that equation for x. We get x is equal to 1. And that's our critical number. And we just want to check, is that actually in the domain of our function here? Yeah, I can plug 2 into this. I get something that makes sense. 2 times 1, perfectly fine. Minus 1 squared, yeah, I get 2 minus 1 is 1. So it is in the domain. Sometimes we might run into issues where if we find a number here, but then when we try to plug it into the actual function, we get division by 0, and that becomes an issue. So we just want to check, is this in the domain of, not f, but q? Is this in the domain of our original function? And yeah, it is. So if we are going to have a max or a min, this is where it's going to happen. It's going to happen at x equals 1. So now we've located, or we have a possible location. So remember, the critical numbers are just possible locations where we're going to have a max or a min. But we have to figure out, do we have a max, min, or neither? But this is the only place that it could happen. So the next step then is to actually classify the critical number. And we have 2 options for how to do this. First derivative test or second derivative test. Either one probably will work here. Sometimes the second derivative test is a little bit quicker. So let's do that. But if you wanted to do first derivative test, perfectly fine. So let's calculate the second derivative, because we're going to do the second derivative test. So when we calculate q double prime, I get negative 2. Derivative of this 2 here is 0, and derivative of negative 2x is just negative 2. So my second derivative is always negative 2 here. So, even if I take my critical number, which in this case was 1, and I plug it in, well, the second derivative is just a constant function, so I'm always getting out negative 2. So when I plug in 1, I get negative 2. Okay. What does that mean? Well, if we try to remember what the second derivative test says, draw in what that negative means in terms of concavity to help you remember. So negative means concave down. Draw in the concave down shape, and there you can see we're going to have a local max. A local max at x equals 1. And actually, we only found one critical number. This function is defined for all real numbers. So not only is this the local max, it's the absolute max. So a little bonus there is because we only found one critical number, not only is this a local max, this is an absolute max. And there's only one critical number on our entire interval from minus infinity to infinity. All right, so there we go. We've located where our function has a possible max min, and then we use the second derivative test to actually say, or to classify it, there is definitely a local max going on here. And because it was the only critical number, not only is it a local max, it's the absolute max. And so the last step here is just to make sure we're actually answering the question. So for our purposes, we want to find the maximum, and it's kind of implied here, the maximum value of this function. So that's really what we're looking for here is the max value of our function. So let's take x equals 1 and plug it into our function. What do we get? So q of 1 is equal to 2 times 1 minus 1 squared, which is 2 minus 1, or 1. So this is the absolute largest value of our function subject to this constraint. All right. So this kind of just illustrates most of the steps and definitions that we're going to be using for these applied optimization problems. So as we'll see in the next few examples, really these types of problems start they're kind of word problems. And so a lot of our work, apart from the calculus here, a lot of our work is just going to be setting up these two equations. Once we get these equations, this process becomes a little bit more straightforward. But a lot of our work is going to be first figuring out, well, what are these two equations? We're not necessarily going to be given these equations. So we'll see you in the next example. We'll see you there.